VA plus 4 VB equals 0. And then if we plug in 2 meters per second as the speed of VA, we get that VB is equal to negative 0.5 meters per second, and it's negative because we're assuming that down is positive for this one. You could assume it the other way, you would just get the other sign, so it doesn't matter, we're just assuming that this is down, so we would write it as 0.5 meters per second, and we're going up, since we assumed down is positive. Okay. Is any of that confusing? Any of that need clarifying?
I think what I'm looking for is like the strings. I don't know how to find out which strings are for like what length that is.
Okay, yeah. So this one is slightly more difficult to like look at. So basically, we always want to look at like each individual chord, because that total length is not changing. So this one, because it incorporates the hooks like in the distances, it's kind of difficult to like look at it and be like, oh, that's SC. But we know that from here to here is always going to be a constant length. So this part is going to reference SC, and this part is going to this one is going to reference SB. Yeah, so just like, did that make more sense?
Yeah.
Okay. Okay, moving on. Some projectile motion. Okay. Take a minute to copy down anything you need to. All right, so we're told that the velocity at the starting point at the origin is 25 feet per second. The exit is oriented at 30 degrees from the horizontal, and we want to know how high the wood chips are landing on this pile over here, if the pile is 20 feet from the tube. So, first, what I think is generally helpful is to find the x and y components of the velocity, just so we have them. So the starting velocity in the x direction is going to be 25 feet per second, and then cosine 30 degrees, and in the y direction is just sine 30 degrees. 25 feet per second, sine 30 degrees. And we have 21.65 feet per second and 12.5 feet per second. Okay. So we also thinking about acceleration, since we're doing kinematics and we can kind of assume that we might want to know something about the acceleration. We're not told that there's any acceleration on any of this, so we can assume that it's just gravity and then nothing in the x direction, and that there is no horizontal acceleration. So we know that in the x direction is 0, and in the y direction it's gravity. So I'm going to assume that down is negative. Generally, that's what I assume, so here we go. And so 32.2 feet per second squared. Sorry. All right, so we want to eventually know how high the chips are landing. So I would use the equation. It's on your equation sheets. Y equals y naught plus velocity in the y times the time times 1/2 acceleration in the y direction times the time squared. So if we look at this equation now, we know acceleration, we know the velocity in the y direction. We don't know, we're trying to find how high up it lands, and we also don't know the time that it takes for this to get there. So that means we need some other equation that can help us tell what time it takes for the chips to get there. So then I would go look at the x direction. And so the x direction, we have x is equal to x naught plus x naught t plus 1/2. So same equation, just in the x direction. We already know, we know the velocity, we know our starting distance, which is 0. We also know the distance that it's traveling, which is 20 feet, we're told down here. And then we also know that this term goes away because there's no acceleration. So we have everything but time, so let's solve for time. All right, so we have 20 feet equals 0 plus 21.65 feet per second times time. And then just divide 20 by 21.65 feet per second, and then we get that time is equal to 0.9238 seconds. So now we take this and plug it into here, and we get y is equal to 4 feet, which is our starting distance up here, plus 12.5 feet per second times 0.9238 seconds plus 1/2 times negative 32.2 feet per second squared times, and that got squishy. And then just plug that into the calculator, and you get 1.81 feet. So, so that's our answer. Yeah, it's not overly difficult, this one. So, any questions? Okay. We're going to do this one next. All right, so for this one, we have two planes that are, one is flying along a straight path and the other one is flying along a circular path. And we're trying to determine velocity and acceleration of B as measured by the pilot of A. So we're trying to determine B with respect, the velocity and acceleration of B with respect to A. So this is on your equation sheets, but we can, for this one, we're going to use that VB is equal to VA plus VB with respect to A. So velocity is pretty straightforward. We already know that we have the velocity of A here, and the velocity of B is here. And there's only a y component of their velocity in both directions. So 600 kilometers per hour is equal to 700 kilometers per hour plus VB with respect to A. Solve for VB with respect to A, and we get negative 100 kilometers per hour. So that just means that we're going in the negative y direction. So VB with respect to A. And we're going that way. Okay, so now for acceleration, we're given acceleration of A down here, and since A is flying along a straight path, we can assume that we only have acceleration in the y direction. But the other plane is flying in a circular path, so we're not only going to have some acceleration in the y direction, we're also going to have a normal component. So there's going to be tangential and normal components of acceleration. So we're given the tangential component. Sorry, my arrows are making this confusing. We're given the tangential component right there, and we need to figure out the normal component. We are also given the radius of curvature of the plane's path right here. So we can use the formula that the normal component of the acceleration of B is equal to the velocity of B squared over the radius of curvature, which in this case is, they use rho B. So that's 600 kilometers per hour squared, and then divide by rho B, which is 400, and we get 900 kilometers per hour squared. So then we're going to use the same equation that we use for velocity, but just for the acceleration. So the acceleration of B is going to be equal to the acceleration of A plus the acceleration of B with respect to A. And so for the acceleration of B, we have two components. So we have the normal component, which is the x direction, so that's going to be 900 kilometers per hour squared I, and then minus, because the acceleration of B is in the negative direction, minus 100 kilometers per hour squared, and then j hat, and that's going to equal our A component, which is 50 kilometers per hour squared, j hat, we only have something in the y direction there, and then plus a with respect to b. And again, just solve for a with respect to b. And so we add like components, so add i's and add j's, or you can combine like components. And so then we're left with the velocity of b with respect to a is 900 I hat minus 150 j hat kilometers per hour squared. We're also asked, we're just asked for the acceleration, but we want to, but we can also represent it in magnitude and like angle, as this is indeed like the acceleration. It's the full answer, but we can represent it in magnitude and angle. So to get the magnitude, the square root of the sum of the squares, so 900 squared plus 150 squared. And we get 912 kilometers per hour squared, and then the inverse tangent of 150 over 900, and we get 9.46 degrees. And so our I component, our x component is in the positive direction, our j component's in the negative direction, so that means our angle is referenced on this side of the x-axis. And when you're like representing things in like magnitude and angle, make sure you draw a diagram as to what theta, like where theta is, because it could be in reference to anything. So like just reporting it as 9.46 degrees does not really tell you where it's in reference to. You need to always draw a picture if you're, or say like with reference to below the x-axis.
Wait, why is the angle below the x-axis?
So we have our, if we look at our vector here, we're in the positive x direction, so we're going this way, and then we're in the negative y direction, so we're also going down. So so we're going across in the positive direction and then down, and so our resultant is below the x-axis. Okay, so the next one, we have two cars, and they're traveling at their own respective speeds, and we also are given some information about their accelerations. And similarly to the last problem, we are determining velocity and acceleration of B with respect to A. So we're going to set up a similar equation that we did last time. So VB is equal to VA plus VB with respect to A. So the velocity of B we see over here, it's just in the negative y direction. So we have minus 12 meters per second j hat, and that's going to be equal to our the velocity of A. So that's we have here is the velocity of A, and we're given what angle that's at. So this will be 60 degrees here as well. So we have minus 18 cosine of 60 degrees I hat. That is a bad looking eye. And then minus 18 sine 60 degrees j hat. And then plus VB with respect to A. And so if we combine the like directions and solve for VB, we get that VB with respect to A is 9I plus 3.588 j hat. That does not look like a 3. Okay. And then meters per second is our units. And again, if we want to do magnitude and angle, the magnitude of VB with respect to A is 9 squared plus 3.588 squared, and that's going to give us 9.69 meters per second. And if we take inverse tangent, we get 21.7 degrees. And again, looking at our vectors, we're both in the positive direction, so our angle is in reference to the horizontal, is positive from the horizontal x-axis. So now we need to figure out acceleration. The car A up here, we know its acceleration is going to be, it's decreasing in speed, so it's negative 2 meters per second squared, and it's also at that angle again. So we'll have some both I and j component there. And then car B, we're told, has a is it increase? Okay, yes, increase in speed of 3 meters per second squared. But it's also coming out of a curve, and we're told that that curve has a radius of curvature of 100 meters. So again, we're going to also have some normal component to that acceleration. So I'm just going to write out the accelerations of each car first. So we know that the acceleration of A is 2 meters per second squared cosine 60 degrees I hat plus 2 meters per second squared sine 60 degrees j hat. And then for B, we have the tangential component, which is 3 meters per second squared in the j direction. And then our I, it's 12, it's not 12, it's 3. Okay. And then in the I direction, we're going to use the same formula. A, B in the normal direction is going to be VB squared over rho. So the velocity of B is 12 meters per second. And then square that over 100 meters is our radius of curvature. And so we're left with 1.44 I hat plus 3. Sorry, I did my signs wrong. Okay, these are both going down, so these are both negative because I referred to this one as being in the positive direction here, and that's going up. So these are both negative. Okay. All right, and then if we do the same thing as before, we have the acceleration of B equals the acceleration of A plus the acceleration of B with respect to A. And we're going to solve for the acceleration of B with respect to A. Okay, and so our final answer is negative 2.44 I hat and negative 4.732 j hat. Yes.
For that angle you got, 21.7.
Mm-hmm.
Could you draw where that angle is on
Like on the.
Yeah, because I don't really get what that's supposed to represent.
So we're just looking at so that angle is basically the angle of travel of car B, like as if you were looking at it from car A. So
Okay.
it's kind of difficult to draw, but it would be like, yeah, so.
So if you drew a diagonal line going through B, that's okay.
Yeah, it would be like, be going like this way, I guess. When we're in the positive, that's a little steep, but anyway. Okay. And if you're asked for magnitude and angle, not just to leave it in vectors, you do the same thing. So square root of some of the squares for the magnitude and then find the angle using inverse tangent. All right, so we have about 5 minutes. I'll do one other quick one and then we'll be all done for the day. So we can do this one. All right, so we're looking at a train and a car, and we want to know the magnitude and direction of the velocity of the train relative to the car. So looking at it from the car, what is the magnitude and direction of the velocity of the train? So same thing as before. The velocity of the train is going to be equal to the velocity of the car velocity of t with respect to a. Okay. So we know that the train is traveling only in the x direction. Kind of hard to see, but it is labeled on the thing. So we have 60 miles per hour j hat, and that's gonna be equal to the components of in the x and y direction of the car, and this one's labeled pretty clearly. We have a 45-degree angle, and we're traveling at 45 miles per hour along that angle. So 45 and then we're going to solve for dt with respect to a. And then we get 28.2 I hat minus 31.8 j hat in miles per hour. And this one specifically asks us for magnitude and direction, so we want to get both the magnitude and the angle. So square root of the sum of the squares. And that's 42.5 miles per hour. And our angle that's going to equal 48.5 degrees. Okay, and if we look at our vector up here, we're going in the positive x direction, but the negative y direction. So our angle theta is going to be below the positive x-axis. Okay, that one was fairly quick. Okay, so we got about a minute. I'm not going to do anything else, but so for next week, I'll bring in more of the ones that are like your homework, because these are just ones from the book, but I'll bring in ones that are closer to like maybe the ones like Dr. Deal would assign. And tell your friends, make sure that more people come. And if you have any comments, questions, please let me know. Thank you, everybody. Have a good weekend.